Hello everyone, my name is Chen Hong Wang. Welcome to the tutorial. This module is about differential privacy. Throughout this module, you may expect the following contents: the desiderata for defining privacy, the basic definition technical knowledge about differential privacy, the existing solutions that integrate differential privacy into database design, as well as some open challenges. Let's start with a well-known privacy breach example for Massachusetts governor. So assume the hospital publishes certain medical data where they anonymize important identification information, such as the name and the social security numbers. However, attackers can still infer sensitive information by combining the medical data with another public table, which is the voter list. Then, according to some crazy identifiers, the attackers can identify the record in the medical data that belongs to the Massachusetts governor. So the crazy identifiers are pieces of information that are not themselves unique identifiers, but are sufficiently well correlated with an entity that they can be combined with other crazy identifiers to create a unique identifier. So for example, you may not be able to identify an individual by using only the zip code, the DOB, or the gender information. But by combining these three attributes together, almost 90% of US populations can be uniquely identified. So we then claim these three attributes are crazy identifiers. And here's one solution for this, which is called k-anonymity, which could avoid linkage attacks. The k-anonymity works as follows. If every row corresponds to one individual, then every row should look like other k-1 rows based on the crazy identifier. Here's an example about full anonymity. And if we consider the zip code, age, and nationality are crazy identifiers, then each row should look similar to other three rows with the crazy identifier attributes. However, this k-anonymity setting may have issues when the adversary has some background knowledge. For example, assuming the adversary knows that Emiko is a 25 years old Japanese who currently lives in zip code 13053. And based on this information, the adversary learns that Emiko's information is contained in the first four tuples of the given table. Without additional information, the adversary is not sure whether Emiko caught a cancer or has a heart disease. However, it is well known that Japanese has an extremely low incidence to have a heart disease, and therefore, the adversary can conclude with nearly certain that Emiko has a cancer. And this is a type of inference attack that utilizes background knowledge. There are many types of attacks that using background knowledges. There are attacks against Netflix data, against search law, and against social network. Therefore, the first desiderata for privacy definition is to resilient from background knowledge. That is, a privacy mechanism must be able to protect individuals' privacy from attackers who may access the background knowledge. The second problem of privacy is that many organizations may think their data are private because they perturb the data and make some parameters of the perturbation secret. However, this is a very strong assumption. And in a general privacy definitions, we should assume that the attackers could somehow obtain those secrets and they are well known about how the algorithms works. So the second desiderata for privacy definition is to achieve privacy without obscurity, which means that attacker must be assumed to know the algorithm as well as all the parameters used to achieve that algorithm. The third major problem of privacy is the post-processing. Let's take a look at this example where it releases an aggregated statistic for a group of people according to two attributes, the age range and the race. So to achieve the k-anonymity, for any counts that are less than k, they are suppressed without revealing the exact number. Okay? However, by doing some simple math, the suppressed value can be computed, and this leads to a privacy breach. So the third desiderata for defining privacy is the post-processing property, which means post-processing of the output of privacy mechanism must not change the privacy guarantee. The fourth problem is multiple release problem. For instance, if two hospitals both uses k-anonymity to release their own data, one uses 4 anonymity, another uses 6 anonymity. Now, let's assume Alice visited both hospitals and she is 28. Can you deduce Alice's medical condition? And the answer is yes. And this implies that the 4 anonymity plus 6 anonymity does not give you another k anonymity. Right? So that is a problem about the multiple release. And so here we need to introduce an important theorem, which is the database reconstruction theorem, where informally, if too many statistics are released too accurately, the vast majority of the records in the hidden database can be reconstructed. And the attack that finds the database D that best matches with released statistic over a hidden database is called the reconstruction attack, and which has been successfully demonstrated by US census in 2019. So in order to ensure the utility, a statistical database must leak some information about each individual. So we can only hope to bound this amount of disclosure, but we cannot eliminate them. Therefore, according to the reconstruction theorem, there is a limit on number of queries that can be answered. So the last desiderata for defining a privacy is the composition over multiple release, which allow a graceful degradation of the privacy with multiple invocations on the same data. Now let's take a look at some basic concepts for differential privacy. In general, differential privacy is not an algorithm or a property of the algorithm's output. It is a property of the algorithm itself. So let's keep this in our mind and we will start our discussion. Let's start with an illustrative example, and we think about the setting where a trusted data curator collects data from data subjects. Sample curator can be a hospital, and the data subjects can be a patient for that hospital. In the meantime, there is a group of external analysts who may wish to make some analysis over the data managed by the data curator. In a default way, the analyst can ask the data curator to evaluate a certain algorithm over their collected data and release the output back to them. However, the data subjects may be concerned about their privacy. For example, the Bob is a patient of the hospital, and he may want to know that could releasing the result of the algorithm A reveal his risk of her disease? And could this lead to an increase of his insurance premium? And to solve this, we need to formulate the concept of the privacy. Then we start with our first attempt to define the privacy. And if we think a mechanism is private, if an attacker cannot learn much about an individual beyond what they can already know. And apparently, this is not a good definition, as the learning principles of nature should not be considered as a privacy breach. So we start with a second attempt, and we consider an algorithm. So if the information that we can learn about an individual from this algorithm is similar to what we can be learned from an opt-out word, where the individual is absent from the input data. And in that case, we may say that the mechanism is private, or this is a privacy-preserving mechanism. Okay? And then, if we formally define this, we will introduce a new term. It's called differential privacy. Then we consider a mechanism A satisfy differential privacy if for any pairs of inputs that differ in one row, and for any possible output, the adversary should not be able to distinguish between that pair of inputs based on the outputs. Okay. And so why we consider pairs of databases that differ in one row? Because this simulates the presence or absence of a single individual or records, which means that it can capture the membership of the records. Right? And usually we call such a pair of databases that differ by only one record as the neighboring databases. Now, the second question is why we consider the all pairs of the inputs, or the all possible pairs of the neighboring databases. So as the privacy guarantee should hold no matter what other records are. And that's why we should consider all pairs of the neighboring databases. And what is the epsilon stands for? The epsilon here is the privacy parameter. It controls the degree to which the neighboring databases can be distinguished. And smaller epsilon means the advance to distinguish between neighboring databases is relatively low, which implies a better privacy. And usually better privacy means a worse utility, and this will be discussed in a later section. Now let's take a look at a typical approach that achieves epsilon differential privacy, which is called Laplace mechanism. So the analyst can make some query request to the curator who manages a private database. And such query can be a counting query which aggregates some results. And the aggregate computes the query over the private data. However, instead of releasing the exact query answer, the curator distorts the results with some differential with Laplace noise and reveal the noisy answer back to the analyst. So one major question is, how much noise should be added for privacy? And the general question is, the noise added should be proportional to the global sensitivity. So, and the global sensitivity is defined as, for a query is defined as the maximum output change for any pairs of neighboring datasets. In adding Laplace noise proportional to the global sensitivity to the true query answer satisfies differential privacy. Okay, let's take some examples to learn more about the query sensitivities. And the first query example is a counting query. For instance, the query that counts how many people having flu in the given relation here. And knowing that adding or removing one record from the database D, the counting query outputs only changes at most one record. So therefore, the global sensitivity is 1. And to answer this query, the curator first computes the true counts, which is 2, and adds Laplace noise proportional to 1. Another example is the summation query. And for instance, the query that sums the total usage of drug X. And if we assume that all values for drug X usage is a real value within range A and B, then we know that the global sensitivity is equal to the maximum possible value of X, which is B. And similarly, to use Laplace mechanism, the noise should be added proportional to B. In general, Laplace mechanism works for any function that returns a real number. To learn about the utility, we formulate query error as the expectation of the square root difference between the true and the noisy query answer. Then we can learn that the error is actually the variance of the Laplace noise added to the true answer, which equals to 2 times square of the global sensitivity divided by the square of the epsilon. And it's not hard to see that a large global sensitivity or a smaller epsilon implies higher error, which is less utility. And recall a statement that we have discussed earlier, a better privacy means a smaller epsilon implies worse utility. Okay. So from here we can conclude there exists an accuracy-privacy trade-off for Laplace mechanism. And actually, Laplace mechanism is not a unique one. There are many differential privacy algorithms, such as exponential mechanisms, randomized response, Gaussian mechanisms, and so on. and each of them gives a different accuracy privacy trade-off. We have learned how to respond queries in a differentially private manner. Now let's talk about how to release multiple differentially private queries and how privacy is composed. The first theorem is sequential composition theorem. And it says that if we apply multiple differentially private mechanisms over the same database, and then the total privacy budget equals to the summation of the privacy budget of each sub-mechanism. In other words, if we release multiple differentially private queries, and then the total privacy cost equals to the summation of the privacy budget that is allocated to each sub-queries. The second theorem is post-processing, and it states that applying any operations over the output of any differentially private mechanisms does not change the privacy guarantee. And in other words, if we already responded some query in a differentially private manner, and then any post-processing operations over that query answer will not change the privacy parameter. So far, we have talked the basic definitions and concepts of differential privacy, and actually, differential privacy has widely adopted by various real-world use cases. And more importantly, the additional tools and packages that supports DP experts, programmers, and even non-expert users, which is a positive sign. Well, one of the big issues that standard databases cannot handle is privacy. And in the next part, we will introduce integration of differential privacy into DB design. And fortunately, there is actually many works that have already done this in practice. And some nice thing about the system is that they leverage the standard query language in database system, and then you can actually answer a large class of queries whose sensitivity can be automatically analyzed by the system based on a set of rules. So here is a very simple example. And assume if you have a person table containing individual attributes information, such as person ID, gender, family, or geolocation information. And if I just want to ask how many people from North Carolina, we can formulate the query as an execution plan and then analyze the sensitivity or stability of each operator and get an overall sensitivity, which is pretty straightforward. The previous example is pretty straightforward, and most of the systems have already implemented this. However, what if we group by in the end of the query? For example, we would like to count the number of individuals and group by the geolocation information. Based on the given person table, we know that all individuals are from 3 states. Therefore, the group by results will also show that only 3 states have data, which leak the active domain information. There are some existing solutions for this problem. That is, we can specify the group by keys, or we use a predefined partition. For example, when we group by the geolocation, we will use all states rather than the active states. This opens up a new general research problem of designing a private data manipulation language that can handle related subqueries. And apparently, this requires additional specification of privacy budget or accuracy. Another question is, what if multiple tables are stored? As in practice, when you look at a lot of structured data stored in hospitals or in large corporations, you rarely find just a single table. For instance, in addition to the person table, we also maintain a household table. An individual in person table may have a corresponding records in the household record. Similarly, if we follow the same query execution plan as we discussed in previous slides, we can obtain the sensitivity as 1. Since adding or removing one of the rows in the person data, the query output changes at most 1. Now, what if we remove one row from the household table instead of the person table? To analyze this, we rewrite another query plan. We first apply a filter on the household table that filters out the rows with geolocation equal to North Carolina. Then apply join with the person table. Afterwards, we get a count. By adding or removing one row in the household table, the filtered results changes by at most 1. But the joint output changes may greater than 1, since one household may have multiple corresponding entries in the person table. As a result, the overall sensitivity will be the maximum joint multiplicity. And according to the analysis, we find out that by removing rows from different tables, we turns out to obtain different sensitivity. And moreover, by removing rows in different tables, the privacy objects are also different. For instance, removing rows in person table preserves the privacy of individual person, but for the household table, the privacy is preserved for a single household. So different works may consider different privacy objects. For instance, PinQ and Flex only consider a single row in the table, while Google DP paper enforces the user-level privacy, where the privacy is preserved for each individual. Private SQL then provides a more complicated private object which is based on a foreign key constraint. For many cases where data are complex, it's pretty common that there exist many different privacy objects. For instance, for graph data, we may have age privacy or node privacy. And in the given example, we may have person privacy and household privacy. To automatically handle this case, in private SQL, the authors propose a semantic privacy notion called policy. It defines one of the relation tables to be the primary object, and then it can leverage the foreign key constraints between the tables to track which tables are also protected, and calculate the sensitivity of a query correctly. But the current limitations are the system only considers select foreign key constraints. Let's take a look at how private SQL can be used in our given example. Consider we set policy as person, meaning that person table is the main private object. And given a query that search individuals with age greater than 17, we learn that this query is only applied over the person table, which is the primary private object. And therefore, we can write a query execution plan as follows. We first apply a filter operations over the person table that filters out all rows with age greater than 17, and then we return the retrieved outputs. And knowing that adding or removing one row from the person table, the resulting query will only change by 1. Thus, we obtain the sensitivity on the policy person equal to 1. However, if we think of the policy is said to be household, where the primary private object is changed to the household table, then if we calculate the sensitivity using the same execution plan, then we will obtain a wrong sensitivity, since the query execution plan does not apply over the primary private object, which is the household table. To address this problem, the query needs to be rewritten by a semi-join operator, and the resulting execution plan is as follows. First, a semi-join operator is applied over the person table and the household table, followed by a filter operator that filters out all rows with age greater than 17, and then returns the outputs. And based on the new query execution plan, changing one row in the household table may lead to more than one result affected in the semi-join output. Thus, the sensitivity for semi-join operators equal to the maximum join multiplicity. In addition, as the filter and the search operators have sensitivity bounded to 1, therefore we obtain the overall sensitivity equals to the maximum join multiplicity for semi-join operator. So what else could go wrong here with the multi-relational database? What if the sensitivity of join query is extremely high? And what if the maximum join multiplicity is not public? Fortunately, there are some existing solutions for this. For instance, PinQ uses grouping before join to bound the sensitivity for the join operator. The Google DP paper proposed a contribution bounded approach which manually specifies an upper bound for the join multiplicity. Flex consider using smooth sensitivity, while in private SQL, the authors use truncation with an automatically learned threshold to solve this problem, which offer a more accurate sensitivity calculation approach. The main idea presented in private SQL is to have a truncation operator to bound the maximum multiplicity of the join key. For instance, when computes the semi-join between household table and person table, it first applies a truncation operator to the person table, which restricts the maximum times a record in person table can be joined with the household table. And here we just bound it as a k. And therefore, the sensitivity of the semi-join is then bounded by k. And the following filter operator has a bounded sensitivity equal to 1. In general, we thus obtain an overall sensitivity for the entire query that is k. So as a summary, there are various existing solutions for handling join queries with unbounded multiplicity. For instance, we may utilize the smooth sensitivity, the truncation, sampling, or use the key tracking approach proposed in the private SQL paper. And additionally, there are some open questions as well. For instance, we may be interested in which algorithms to use. Under what circumstance one algorithm is better than the other one? And also, how to physically implement differential privacy into DBMS is also another interesting problem. Some subproblems for this topic includes how to support key tracking in the query plan, and how to efficiently compute tighter sensitivity upper bound for better accuracy. We may also face problems when dealing with multiple queries, and this is also a critical point where the integration of differential privacy with databases may go wrong. For instance, if we issue unlimited number of queries, and according to the composition theorem we have discussed earlier, we know that we either incur unbounded privacy loss or we have to stop query answering for after certain rounds of response, which is not ideal in the real-world implementation. To address this problem, there is some work that propose the approach to generate a general differential private view for answering multiple queries, or catch historical query answers, which is used laterally to respond to future queries. However, there are still some open questions here, like how to ensure consistency between each of the queries, how to allocate privacy budget among different queries, and also how to pick the proper differential private algorithms for answering multiple queries. Additionally, there might be some general implementation issues as well. For instance, the first problem is how to handle the side channel attacks, which means that the adversaries may be able to observe answers to their questions, respond time, system decisions to the execution query, or deny it. And in some cases, by observing their execution side channel leakages, the adversary can actually infer some critical information about the original database. The second point is the randomness and floating point issues. The randomness implementations in differential privacy is a big issue. For instance, how we could guarantee that the randomness is honestly generated. So far, we have covered all key aspects of this tutorial, and let's summarize it. We start with the principles for defining privacy, and then learn about the basic concepts for differential privacy. Lastly, we explore the system designs that integrate DP with databases. As per the current design for adopting DP to databases, there are some interesting open questions. The first open question is how to design private data definition and private data manipulation language. More specifically, how to protect the privacy at a correct resolution, how to prevent unsafe and non-private query being executed, and how to provide a better accuracy for complex queries. Secondly, even though there are many existing solutions that integrate DP to database design, there are still some remaining problems, such as how to add the DP on the top of existing database design, and how to re-implement DP components for better utility and performance. So that's all for this tutorial module, and please feel free to ask any questions.